This video is discrete random variables binomial distribution. Okay. Has anybody heard of the restaurant Whataburger? It's a restaurant chain in the South. They sell hamburgers. Well, let's say that Whataburger is running a contest, and if you buy a burger, it comes with a pull-off tab. 25% of the tabs say you win a free small fry, while the remaining tabs say better luck next time. So if you buy a burger, your chances of winning are the same as the percentage of tabs that say you win. It's 0.25, which is the same as 25%. However, if you decide to buy, what if you decide to buy burgers for 10 of your friends? What's the probability that exactly 3 of them will win a small fry? Or what is the probability that half of them will win a small fry? What is the probability that all of them will win a small fry? So all of these questions can be answered when we recognize that this problem is an example of what is called a binomial random experiment. And so we're going to talk about something called binomial random variables. So a binomial experiment, a binomial random variable comes from a binomial experiment, and a binomial experiment has these characteristics. First, so there's four main ones. First, it has a fixed number of trials. The number of trials we'll use a lowercase n to represent. There are only 2 possible outcomes. We label one a success and one a failure. Now, you may have more than 2 actual outcomes, but you can put the outcomes into 2 categories, success or failure. For instance, in a bag of M&Ms, you have blues and reds and browns and greens, so and some other colors. But let's say you win a prize if you reach into a bag of M&Ms and you pull out a blue. So technically, even though there's multiple colors in the bag, we can say that a success would be pulling out a blue and a failure would be pulling out any other color. So you can create it to be 2 outcomes. When we label one a success and one a failure, the probability of a success will be lowercase p, and the probability of a failure will be lowercase q. Now, probability of a failure is the complement of the probability of a success. So we could use the rule of complements, 1 minus p, to find q. So q will be equal to 1 minus p. So if p is 0.25, q is 0.75. If p is 0.80, q is 0.20. The third characteristic that we need is that the probability for success is the same for each trial. So one trial occurring is not going to affect the probability of a success for the next trial. And then all the trials are independent. So 4 characteristics that need to be met: a fixed number of trials, 2 outcomes, a success and a failure. Probability is the same for a success for each trial, and trials are independent. Now, I do have a number 5 listed here. This is a characteristic, but it's not one of the 4 that we need to have met to be a binomial distribution. It just says that random variable x describes the number of successes. So x describes the number of successes. So if a success is pulling out 10 M&Ms, and a success is drawing a blue M&M, you could have 0 successes, so no blues, or of 1 blue, which is 1 success, or 2 blues, which is 2 successes, or 3 blues, 3 successes, all the way up to 10 blues, and that would be 10 successes. So let's look at example 1, are these binomial? Decide whether each of the following is a binomial random variable. A coin is tossed 10 times. Let x be the number of heads. Alright, first, there needs to be a fixed number of trials. The coin is tossed 10 times, so that gets a check. Number 2, there has to be 2 outcomes, a success and a failure. So let's see, a success would be heads, a failure would be not heads, in which case would be tails. Number 3, so that one, hold on, number 2 was check. Number 3, we need to have the same probability for every trial. So the probability of success, P, what's the probability of heads? 1/2. And that would be the same for every flip. So we'll check off on that as well. And lastly, the probabilities need to be independent. So are the trials independent from one another? So is flipping a coin, flipping heads for the first trial, going to affect the probability of flipping heads on the second trial? No, the probability is going to stay consistent and stay 1/2 for every trial, so it is independent. So that means check, all 4 are checked off. So is this a binomial random variable? Yes, it is binomial. Alright, 5 basketball players attempt a free throw. Let x be the number of free throws made. So since 5 basketball players attempt a free throw, there's 5 throws. So number 1, fixed number of trials is 5. We're good there. 2, we need a success and a failure. So a success would be making the basket, and then a failure would be a miss of the basket. So that's 2 outcomes. We're good there. Alright, is the probability the same for every trial? So hypothetically, in the perfect world, the probability of making a basket would be 1 out of 2 because there's 2 outcomes. You can make the basket, you can miss the basket, that's 1 out of 2. But in actuality, there's so much more that goes into that. What is the skill level of these 5 basketball players? Are they professional basketball players? Are they on a basketball team? Are they amateurs? Are they brand new? Have they never picked up a basketball before? So the point is, some players may have better chances of making a basket than others. I know if I were to be asked to do a free throw, there's a good chance I'm not going to make a basket because I'm not great at basketball. Whereas someone else might make a basket almost every time they throw a free throw. So the probability is not the same for every trial because we have 5 different basketball players that are throwing. If it was the same person throwing, then the probability that they would make the shot would be the same because they were the same person with the same skill level doing 5 shots. But this is 5 different basketball players making 5 different shots, so definitely those 5 would have different probabilities. So because this one, this characteristic has not been met, it is not binomial. Alright, and let's look at the third one. A random sample of 250 voters is chosen from a list of 10,000 registered voters. Let X be the number who supports the incumbent mayor for re-election. So the number of trials is 250 because they are choosing 250 people. So each one of those people counts as that they choose counts as a trial. And there is a success and there is a failure. A success would be that they support the mayor, and a failure would be that they do not support the mayor for re-election. So both of those are good. The probability that a person chosen at random would support the mayor is going to be the same as the relative frequency of the population, basically the proportion of the population who support the mayor. So that is going to be consistent as well. That's going to be the same throughout. And then last, independent, because the probability is the same for every trial, it is independent. So we are good there. So this one definitely is a binomial distribution. It's a binomial experiment with a binomial random variable. Consider the following. A biased coin has the probability of 0.6 of coming up heads. The coin is flipped 3 times. Let X be the number of heads that come up. Create a probability distribution that lists the probabilities for all the possible outcomes for X. Actually, I think what I'm going to do is I'm going to stop the video here because I only have about 3 minutes left, and that's not enough to go over this slide that we're on. So we're going to end it here, and we're going to pick up with part 2 on this slide.